All right, so I apologize for last week. So let's do this warm up and see how we're feeling on moles and if we can solve this. So we have ammonia can be synthesized by this reaction. And so luckily it looks like they balanced it for y'all. So we have 2 equivalents of nitrous oxide plus 5 equivalents of hydrogen gives us 2 equivalents of ammonia plus 2 equivalents of water. And then so it says starting with 86.3 grams of nitrous oxide and 25.6 grams of hydrogen, find the theoretical yield of ammonia. So I'll give everyone some time to get started.
Is it just me or there are less of us here than when we first started the class?
There is less now.
Not less.
So what steps, and I know you might not be done, but what should we start with and kind of how to approach this?
Figure out how many moles we have of each element.
So we need to find moles of everything, and so that's a good step. So I'm just going to say find moles. So I'll start with our NO. And so what do we get for our molecular weight then of nitrogen monoxide?
Oh, sorry, 30.
So 30, so I just pulled those numbers from the periodic table. I did some rounding. So 30 grams per mole. And we can go ahead and set up our dimensional analysis. So then this gives us kind of moles of NO, but I'm not going to solve it yet, because then kind of the last thing, so what do I do with the moles of nitrogen monoxide? So we solve for that, and then what do we do with that number?
Well, we also need to figure out how, after we convert moles, we also need the amount of hydrogen we have in moles.
So we still haven't taken into account that. So I'll come back to this NO, and I'll just do this setup then for hydrogen.
Wait, isn't it? No, never mind.
So find moles of H2, and so our molecular weight is 2 grams per mole. So we'll set up our dimensional analysis, so 25.6 grams of hydrogen divided by its molecular weight. So now this would give us moles of H2.
Okay, so we need, oh, sorry.
So yeah, so where do I go from here? So right now I just have moles of each if I chose to punch it in, but kind of holding off, yeah.
Well, after we do that, we need to know how many moles, well, we need to know the formula for it. So there's 2 moles of NO for every 5 of hydrogen.
So that doesn't,
So
we could use that.
well, after we convert that, so divide the numbers by 2 and 5.
So I see where you're going, so you
We
can
need to
kind of
figure out
see.
which one is the excess in it.
So we could do that, or there might be a little bit easier way to do it, and we'd save ourselves some work in the future. So instead of comparing NO and hydrogen, what else could we compare? Because you're not wrong, it's just like the longer way of doing stuff. And so we're trying to find, right, ammonia in the end. So what am I really interested in?
Moles of ammonia?
Yeah, so then what would I be comparing? Kind of think back to the s'mores too, right? Like if you have 2 graham crackers, we had 1 marshmallow, and so what would be kind of the comparison here?
Hydrogen and nitrogen?
Well, nitrogen's not an option, right? Like there's no N2. So we can only kind of compare our species here. You can, it's just more work, and I don't want to do that way, because I found that it's confused students more than it helps in the past. So I'm going for ammonia. So what should I be comparing it to? What should I do my mole-mole ratio of? can also look at your dimensional analysis, right? You're going to end up with moles of NO. I want ammonia, so how do I get there? So I'd want to compare NO and ammonia, right? So then that's what I would do next, because we have moles of NO, or at least we will have a number. And then our next step, right, is our mole-mole ratio. And so if moles of NO is on the bottom, or excuse me, moles of NO would be on the top, because that's what we get from here. So then moles of NO goes on the bottom to cancel. 2 moles of ammonia goes on top. And of course, they're in a 1-to-1 ratio, so I didn't really need to do this, but this is good. And so now this would give me moles of ammonia. And so let's go ahead and plug that in. So 86.3 grams, so divided by our molecular weight. So again, that gives us moles of NO now. And we go back to our balanced equation. So if you have 2 moles of NO, you get 2 moles of ammonia. So in this case, right, we have 2.87 moles of NO. So that's going to give us 2.87 moles of ammonia. So now let's hold that thought, because like you were saying, we still need to figure out our limiting reagent. So this is how much we could make, right, from 86 grams of NO. So now let's do the same for hydrogen, except what do I plug in for my mole-mole ratio?
So that third step is just to cancel out the,
Yeah, this step, yeah, you're going from moles of NO to moles of ammonia, right? Because, again, just think back to your s'mores, right? Let's say we had 86.3 grams of our graham cracker, right? We found our moles of graham cracker, then we have to compare using our formula. So if they're in a 2-to-2 ratio, then we know we have the same moles. So that's all that means, right? So it's like if we had 2 graham crackers and then we needed, you know, two chocolates instead for our formula.
and they're always going to equal, so the equations have to be balanced, right? Or is there ever a time where they're not going to be the same?
It will be random, so you don't know. So you have to look at the balanced equation. It just so happened that they're in a 2-to-2 ratio, and so they canceled out nicely. But so then looking at the next one, what would the conversion factor be? What's the mole-mole ratio? Because it's the same thing, except now we'll get moles of H2. So then what would we plug in? Well, we don't care about water though, right? Water's not a part of that at all. But we're still focusing on ammonia, right? Because we still don't know how much ammonia we produce based off of these 2 reagents. So we're still trying to find the limiting reagent.
So would we do the H2 with the NH3?
Yeah, so then we're looking at that one. And then so which one goes on top then? Yep, so then that means we'll get moles of ammonia on top. And so they're in a 2-to-5 ratio. So 5 moles of H2. And so let's see what that gives us. So 25.6 grams of hydrogen divided by our molecular weight. and then times 2 divided by 5. And so I get 5.12 moles of ammonia. And so now, at this point, we can kind of zoom out and compare the two. So question just with rounding. So rounding kind of depends. For things like nitrogen, it's totally okay to do it as like 14. Same with like oxygen, I usually just round to 16, or hydrogen, I round to 1. But then other things like chlorine, where it's 35.45, you'd want to use like at least 4 or 5. So yeah, and I expect discrepancies with rounding. So as long as you show your work, then I know where you're coming from. All right, so now we kind of zoomed out. And so looking at these, so which one produced the least amount of ammonia?
The NO?
So exactly, so the NO. So this means that this would be our limiting reagent. And then from here, we could go on to finish the question. So it asked us for the theoretical yield, so that just means, again, when we have 100% yield of ammonia, and then it's asking in grams, so we can just go ahead and convert this moles to grams. And so what's the molecular weight of ammonia?
Let's see, molecular weight of ammonia should be 17 point,
You go round to 17 probably. So then we can take this 2.87, so again, moles of ammonia. We want to multiply it by its molecular weight, so 17 grams per 1 mole. I'm just drawing it all out. And then that gives you your answer. And so you should have that it should make 48. And look at our sig figs, so it should be 3 sig figs, so 48.8 grams of ammonia. Let's do another one. So we have hydrogen plus nitrogen gives us ammonia. So if I have 33.4 grams of nitrogen and 10.11 grams of hydrogen, how many grams of ammonia will I produce?
this formula doesn't add up? How is it? N2 plus H2 equals N3. No byproducts or anything.
NH3.
Sorry, NH3. H2 and N2.
I never said it was balanced, so
Do we have to balance it?
always.
Okay, sorry. I used confused.
So I see an answer in the chat at least. So what was our balanced equation? Let's start with that.
Three H2 plus N2 equals 2 NH3.
So that looks good. So now that we have this, what did y'all do next? So let's do, we'll find our moles. I'll put mole ratio too. So let's just repeat what we did before. So 33.4 grams of nitrogen. So divided by the molecular weight. So what's the molecular weight of nitrogen? So it's N2 though. So it'd be 14 times 2. So 28, we're all good with that, 28 grams per mole. So 14 from there, so 14 times 2. And then let's go ahead and plug in, right, our mole-mole ratio, because we want ammonia again. So we get N2 from here. So what ratio would I plug in? So 2NH3 over N2. So that looks good. So now let's see how many moles of ammonia we can get from nitrogen. So starting from nitrogen first. So just plug that in. So 33.4 grams divided by our molecular weight. And then times 2. So for this one, I get 2.39.
28 grams at the bottom.
I just forgot the grams there. So moles of ammonia. So that's our first one. So now let's repeat for hydrogen. So we'll do the same. So figure out how many moles of ammonia. So we have 10.11 grams divided by our 2. And then what ratio should we plug in here? So 2NH3 over 3H2. So 10.11 divided by 2 times 3 divided by 2. And so I get 3.37 moles of ammonia. So then which one is our limiting reagent? So the N2. And so now that we know that N2 is our limiting reagent, we can just go ahead and finish the problem out. So convert this to grams again, just like we did before. And so 17 grams per mole for our molecular weight of ammonia. So what do we get for our total mass? You said 40.67 or so? 6.3. So 40.63 grams of ammonia. And looking at the chat, so I assume you got that if you, because your number looks like you have this doubled. So now that we have the correct mass of ammonia, should be good. All right, let's try one more, because I can't emphasize enough how important stoichiometry is. It will haunt you for like the rest of chemistry. So if you don't have this chapter nailed down, like it will not go well. Like I can't stress that enough. Like there's so much math in this chapter. So definitely go home, study it, do this, like do the exercises a billion times until you feel really good. And of course we'll have the most haunting to haunt us. So you could have something that is like this. So determine the products and amount if 22.5 grams of silver nitrate react with, and we'll just say excess magnesium bromide. So let's start with, do we figure out our equation yet? So how would we write silver nitrate? Let's just start with there. So silver's Ag, but then, and then so N, what's the rest of it?
AG3 and then 1 nitrate.
So nitrate though, so do you remember what nitrate is? Because you might be thinking of nitride.
Is it a polyatomic?
Yeah, so nitrate is one of those polyatomic. So you said NO3, right? And so that's NO3 with our -1 charge. So, okay. So there's our silver nitrate written. And then, so how do you write magnesium bromide? What's the formula? Br, but then, so what's the charge on magnesium? So 2, and bromine is usually what? -1. So then what should my formula be to give us a neutral compound? So MgBr2. Good. And then, so now we have to figure out, well, what are my products? And so this is also part of kind of our chapter 5. And we had our lab. So can you guess what the reaction might be? What reaction type, if you were to look back at your lab? It would. So that was an excellent guess. And so you kind of recognize this double replacement. And so let's make a note on the side. So types of reactions to just kind of jog our memory. And so we have this double displacement. And usually that's the type of reaction you'll see, especially. And so, a good hint is we have some sort of cation with an anion and another cation with an anion. And so the most likely thing is that, yes, it would be a double displacement. We can just write the general formula for a double displacement. So you have A and B, so your cation plus your anion plus your new cation and anion, right? We'll just swap partners. There's our double displacement. So with this one, that's all we want to do is swap our partners. So write our new formula. If we put silver now with bromine, so we're just putting our cation with our other anion. And so that would leave magnesium with nitrate. And so now we just write our new formulas that would occur. So what would be silver bromide? How would we write that? So we know bromine has a -1 charge, right? Silver has to be +1 because of how we wrote this nitrate over here. And we also know silver is one of those exceptions. So I see in the chat Ag2Br2, which isn't necessarily bad, but then we see, right, we have a 2 and a 2, and so we could simplify it further to just be in a 1-to-1 ratio. So just AgBr. But save those 2's because we may need them in our coefficients for balancing. And then so how would we write our magnesium nitrate formula?
Would be Mg and then NO3 in parentheses 2.
Yep. So now we at least have all our substituents. And then so now we have to balance it though. So we're at like step 0.5 really. So now how can I balance it?
Can you explain why the NO3 is in parentheses 2?
It's just to show that you would need 2 of the whole NO3 since it's a polyatomic. Since if you were to just write like NO3, 2, right, that's not really clear. It looks like you're just doing it to the oxygen. So if you put that parentheses and you're saying, okay, I need 2 equivalents of that whole nitrate. And then that all balances, right, because magnesium has a 2+ oxidation state. Nitrate, if we look at our polyatomics, has a -1 charge. So again, that's why we need 2 of them. So now how do we balance?
You put a 2 in the first AgNO3, then a 2 in front of the second, the bromine silver.
So I think that looks good. All right, so now we have our balanced equation. And so you should be able to proceed from there. So I'll give everyone a minute or two to see if y'all can finish up. So where do we go from here? So what did we get for our molecular weight then of silver nitrate? Do some math on that one. Let's see, looking up silver, so 107.868 plus nitrogen plus 16 times 3, oops. So did we get like 169 or so for the molecular weight of silver nitrate? See, one nod. So now we have our molecular weight, so 169.868 grams per mole. So now we can get our moles of silver nitrate. So we take our 22.5 divided by its molecular weight.
You would just round up to 170 on 169 molecular weight?
You could. I wouldn't penalize you for that. I just felt like leaving in those digits. I mean, really, too, like as a professional chemist, you wouldn't add up everything on the periodic table like we do. It's good practice, obviously, but normally you would have the bottle in your hand, you would look up the molecular weight, and that's what you would punch in. Or you'd, ask Google to do it for you. There's also like programs that calculate molecular weights, so. And so where were we? So 22.5 divided by molecular weight. So then we should have 0.132 moles of our silver nitrate. And then from there, so I didn't say, because I was keeping it really ambiguous, what to calculate. So I would calculate at least moles of each. So we can find moles of, and in actuality, you would only be really concerned about the silver bromide since, and we haven't gotten there, but this would be coming out of solution. So this is insoluble, so that would be like the solid product that would be forming. This would be in solution. We could still quantify it, but so we could find moles of each. So let's find moles of silver bromide. So then we would just use our mole-mole ratio. So in this case, they're in a 2-to-2 or 1-to-1. I'll set it up explicitly, but you can already tell it's the same. So 2 moles of silver bromide to 2 moles of silver nitrate. So then that gives us 0.132 moles of our silver bromide. And then we could do it for our magnesium nitrate just for fun. So find moles of our magnesium nitrate. So 0.132. Now looking at our mole-mole ratio, they're at a 1-to-2 ratio. So we only get half. So 1 mole of magnesium nitrate is equal to 2 of silver nitrate. So I'll just divide that by 2. So we would have made 0.066 moles of our other product. So we're feeling a little bit better about stoichiometry. So let's hit up our other reaction types. We're kind of running out of time. Yeah, so 0.066 moles for the magnesium nitrate and then the 0.132 for silver bromide. And of course, we could convert that to grams. But
If you put, this might sound silly, but so originally I did 2.5/1 times 1/, I didn't put 70, but the 169.868. And then you put times 1 of the MgO2 over 2 of the silver nitrate, I got the same answer. Would that be okay right now, or would you want me to do these steps?
did you just write it all as like one-dimensional analysis? Yeah, that's perfectly fine. I kind of go back and forth to show both ways. And then, yeah, it's fine if you went to grams on the chat. So as long as you know, right, you can go from moles to grams, grams to moles. All right, let's pick up the pace just a little bit. Chapter 5 is like huge. Chapter 6 is also big. So let's just hit up the other types of reactions we'll see. And so, can you think of any single replacement reactions, or what would that be? What might that look like? So usually you have like some metal plus some sort of ionic compound, Bc, and then usually the metal kicks out this other metal to give you B plus AC. So anytime you see like metals, that's usually a good indication, or HCl plus a metal. So for example, this zinc plus copper sulfate reaction is pretty common. So you would get out copper metal and then make zinc sulfate. So what were other types of reactions that you see? So we had, right, combination. And so those are generally kind of more, they're easier to spot. Usually you have like two things coming together to make one thing. So one example could be iron plus oxygen gives you iron oxide. So something like that. And then we also have, so of course, the combustion reaction. So do you remember how to spot a combustion reaction?
Was O2 and all the products, I think?
So O2 in the reactants, and then what are the products? I like the O2.
CO2 and H2O.
So CO2 plus H2O. So anytime you spot this, and then it should be some organic compound, might have oxygen. And then the last type that we see is this decomposition. So you have one chemical and it becomes kind of two things. That's usually how you spot a decomposition. One of the classic reactions is this dimerization reaction, where you just make two equivalents of nitrogen dioxide. So you can see that would go back and forth, but you start with one thing and kind of make two things. Oh, one last thing before we kind of slightly switch gears is we didn't talk about moles and Avogadro's number. So hopefully you have your mole highway still. I have more available. You can also pull it up. Pull up our mole highway again. And this is why I highly recommend, again, be really comfortable with your dimensional analysis. So the last little bit that we didn't talk about that we need to is this bit right here, is how do we go from particles to moles? And so first of all, we have our conversion factor. And so this means that 1 mole is equal to 6.022 times 10 to the 23rd. And that can be atoms or molecules or even really things. So I could say I have a mole of cookies, and that would mean that I would have 6.022 times 10 to the 23rd cookies. So it's just like a baker's dozen. So it's just an amount. But then if we look at our little conversion, right, we can use our dimensional analysis to go back and forth from moles to particles and particles to moles. So let's do a little practice. So if I have 5.77 times 10 to the 50th gold atoms, how much does this weigh? So give everyone at least a minute to think about it, but just go back to your dimensional analysis, look at your little chart to kind of help you. So what's our first step in this problem? This is what I'm starting with, right? 5.77 times 10 to the 50th gold atoms. I'm eventually trying to get to mass, and so we could look at our mole highway to kind of help us. So we're here, right? We're at our number of particles. We got to get to moles, and then we can multiply by our molecular weight to get to grams. And so, right, to get from particles to moles, we should divide by Avogadro's number. And we can see that if we set up our dimensional analysis. So 5.77 times 10 to the 50th. Now we have atoms. So I want to go to moles. So right, this is my conversion factor here. So if I want moles, moles goes on top. Avogadro's number goes on bottom. So 6.022. times 10 to the 23rd atoms. So now that will cancel, and I'll just pause here for a second. Of course, you could continue going and go from moles to grams all in one line, but pause for everybody. So our first step, again, make sure you use your little E button, make your life easier. So just dividing by Avogadro's number. And so now we have moles. .58 times 10 to the 26 moles of gold. And so now that we have moles, we can go to grams. So that'll be our last step. So 9.58 times 10 to the 26 moles. Pop over to our periodic table. So gold has a molecular weight of 196.96. So 196.96 grams per 1 mole. So then we should get something like 1.88 times 10 to the 29th grams. So is that what chat got? Is that what people got here?
For the answer to the first equation,
Mhm.
are we just dividing 5.77 by 6.02?
Yeah. Is that,
For the exponent, it's just subtraction. So 50 minus 23.
yeah, so you should, if you were doing it by hand, so you could do 50 minus 23, so that would give you 27, and then 5.77, like divided by 6, and so that's where that factor comes in.
So if it's 0.958, are we just moving the decimal point over to get the 9.5?
So you're doing this like just mentally, or?
No, with the calculator. But I mean, like when we divided those two numbers just now, we got 0.958, but then the answer is 9.58. So are we just moving the decimal point over?
Yeah, because you would, what you would have gotten, like if we were doing this kind of by hand, because, and maybe I'm like just kind of confused why you're doing it this way, because I just like plug the whole thing in, right? So,
Well, even, sorry to interrupt, but when I do it on my calculator and I do the scientific notation thing, it doesn't give me 26 like yours did. So I kind of have to do it by hand too, as far as the exponents go.
yeah, so you should work with me after class to figure out how to enter it in, because you shouldn't be doing all that work. So something's going wrong with how you're entering it, and I can fix that on an individual basis. But going back to what you're trying to ask, so we get, right, 27, oh, so times 10 to the 27, and then so divide those, so that's 0.958, so you get, right, 0.958 times 10 to the 27th, but you wouldn't want to leave it in like a 0.9. Like this is an okay answer, but it doesn't follow our sig fig rules or scientific notation rules where you have like one number and then whatever and then your exponent. So yeah, so then you just, by moving it over, that changes that exponent, right? So if you move it over to make it 9.58, now we have to, since you moved it over to the right, that's kind of like lowering it, so that becomes times 10 to the 26. So does that make sense? All right, let's try to at least move on for now. We'll probably have to do more practice if we have time, but we should at least start chapter 6. And by start chapter 6, I mean finish chapter 5. So these oxidation reduction reactions, we're kind of stuck in to chapter 5. So then I put them at the beginning of 6 here. And so oxidation reduction reactions are reactions in which electrons are transferred from one reactant to another. And so these are called redox reactions. And usually you can spot them if we go back to our reaction types. They're basically everything but our double displacements. So if you notice, right, the double displacements, they're just kind of swapping. So our oxidation states won't change. So we could write, these are generally not redox. So you should not be changing oxidation states. I don't want to say never because there could be some weird reaction scenario that I'm not thinking of, but generally double displacements, they're not changing oxidation states. Single replacement, they will be. So anytime you see like a lone metal and it transfers to another metal or becomes part of a thing, that's definitely an oxidation change. So I'll put redox there. Combinations are also usually redox because again you have like two lone elements, then they make some new thing. So that will also be redox. Combustion is always a redox reaction. And then decomposition, this could be kind of depending. So now let's go back. So now we kind of know at least the basics of how to recognize them. So this is again another redox reaction. And so if we have a redox reaction, that means that we have elements that are either losing electrons or gaining electrons. And so atoms that lose electrons are being oxidized, and then anything that gains electrons is being reduced. And so I like this little mnemonic. And so there's two mnemonics that you could use, so depending on your preference. So I'm from Texas, so we like oil out there. So there's oil rig, so you can remember oxidation is losing electrons, and reduction is gaining. So if you're not a fan of big oil, I have another mnemonic. So there's also Leo, and Leo can be a lion or a leopard or whatever your favorite fuzzy big cat is, but Leo goes grr. So losing electrons is oxidation. Gaining electrons is reduction. So either one of those. And so now let's look at how to assign oxidation states. So, sorry, skip down here. So this is important. And so the first rule is, so free elements have an oxidation state of 0. And all this means is anything in its elemental form. And so that means, right, for your diatomics, you're going to have an oxidation state of 0. Your metal should be 0. So everything, again, just in its elemental form is 0. And then, so the next rule is, you already know how to determine this. So monoatomic ions have an oxidation state equal to their charge. So you know, right, group 1, sodium, all those group 1s, they're going to have a 1+ charge. I was hoping for a periodic table. Let me grab one. And so go ahead, right, rewrite those oxidation states if you need. So everything in group 1, 1+ oxidation state, just like we expect. Group 2, 2+. Group 3, right, 3+. Then we have that weird switch here where we have -4 +4. And then -3 for all these for their oxidation state, -2, and -1. So we know how to do that. And then, of course, just to double check yourself, the sum of the oxidation states of all the atoms in a compound is 0, or whatever that charge is equal to. Again, you already know how to do that. And then, so sometimes we'll look at some oddities, for example, in polyatomic ions. And so for this one, so let's break this down a little bit further. So let's say you're looking at nitrate. We're trying to figure out the oxidation states. And so usually you want to base it off of oxygen. And so I'll kind of add in here that oxygen is almost always in the -2 oxidation state. So then we can use this to determine our nitrogen. So we have -2 for oxygen. And so we have kind of our N here, just for our oxidation state, plus 3, since we have 3 oxygens, times -2, all has to equal, right, -1. So we do the algebra. That's why nitrogen has a +5 charge there. And so that's why I also encourage you to at least look at your periodic table with all those different oxidation states. And so yes, these can crop up now, or you could, kind of remind yourself that this column can also be +5 as your oxidation states. And then, so the only time, let me get a sample. So only time oxygen is not -2 is when it's in a peroxide. So if we look at, let's just take H2O2, right? That's just normal hydrogen peroxide. And so hydrogen is usually in the 1+ oxidation state. So we have 2 of them, right? So we have a 2+ charge here. But then, right, normally we would expect oxygen to be -2. Obviously that doesn't work out here. So in a peroxide, oxygen is going to be -1. So that would be the only exception. And so this whole peroxide, its 2 oxygens have a -2 charge, so each one has a -1 charge. So that's one of the few exceptions. But then everything else should be like we expect. So again, right, group 1 is 1+, group 2 is 2+. And then this is kind of like our priority. So for example, you'd want to assign fluorine's oxidation state first, then do hydrogen, oxygen, then group 7, 6, and 5. So kind of leaving, right, group 5, which we're starting to see can be a little bit ambiguous towards the end, and rather you want to base it off of, right, fluorine, oxygen, and your other compounds. So now let's go back up to this little example here. And so we have sodium metal plus chlorine gas gives us sodium chloride. So looking at all their oxidation states. So we know sodium, so it's in its elemental form, so its oxidation state is 0. Chlorine, also in its elemental form, so its oxidation state is 0. And then now when it forms a compound, so we know sodium is group 1, so it'll be 1 plus, so now it's in the +1 oxidation state. Chlorine's going to be in the -1. And then so now we're seeing, right, that sodium underwent oxidation, so it lost electrons. So you can see that again, it went from 0 to +1, so if it's becoming more positive, that means that it lost electrons. And then that also makes sense, right? Because we know sodium, we know it's really reactive, we know it likes to pop off that electron, so it makes sense in this reaction that yes, it'd be the one undergoing oxidation and supplying that electron to chlorine. And then so chlorine goes from the 0 to -1 oxidation state. So it's becoming more negative. So if it's becoming more negative, that means that it's gaining electrons. And so we see that, right, chlorine gains 2 electrons since we have 2 equivalents of chlorine there to give us 2 equivalents of chloride. And then we can say chlorine is undergoing reduction, again, since it gained those electrons. So we can look at this reaction too. So this is, a simple combination reaction. So again, everything starts off in its elemental form in this case, so 0 and 0. So you're adding carbon plus sulfur, and then you make carbon disulfide. And so to figure out the oxidation state of carbon, you want to base it off of the sulfur. So you would look at the sulfur first. So sulfur, group 6 over here, so it's probably -2 oxidation state. So then we have -2, and then we have to get to 0. So -2 times 2 gives us -4. So then carbon has to be 4 plus. And then so we see carbon goes from 0 to a 4 plus oxidation state. So it's becoming positive. So that's why it is undergoing oxidation. So it lost 4 electrons there. And then sulfur here. So we have 2 equivalents of sulfur. Each of those equivalents of sulfur gain 2 electrons. And so we have, right, each sulfur gains 2. So times 2 to give us our 4 electrons being gained. And so the other thing that you kind of notice is the same amount of electrons you lose, you have to gain it somewhere. So your equation should also be balanced by electrons. And then so other terminology. And so the other thing is, right, these oxidation reduction reactions, so they're occurring simultaneously. So sodium is handing off its electron to chlorine, right, all at the same time. And so we can also say that the reactant that reduces an element in another reactant is called the reducing agent. And so your reducing agent, it's the one being oxidized. You can also think of it as supplying the electrons here. And then, so the reactant that oxidizes an element in another reactant is called the oxidizing agent. So this is going to be the element that is reduced. So in this case of sodium and chlorine, so who's the reducing agent? think back to their oxidation states, right? So their elemental form, so 0 and 0, then +1 to -1. So sodium, right, we said that it lost electrons. So what is it doing then? Is it the oxidizing agent or the reducing agent? Reducing, exactly. Right, so the reducing agent, again, it's supplying those electrons, so it makes sense that it's a metal. And then we see that it was oxidized since we go from a 0 to a 1+ state. So oxidation is losing electrons, so it lost electrons. And of course, that makes chlorine the oxidizing agent. All right, we are out of time for today. So lab should be pretty fun. We'll be determining kind of a molecular formula of our unknown salt. We'll be burning some stuff. And so I'll see you all at 7 for lab, and then I'll hang around on stream in case there are any questions. And I know people had questions in class too, so I can address those. So thanks again, and I'll see y'all in lab. And I'm just gonna run to the bathroom real quick and I'll be back.
My question was just on one of the quizzes. There was one where I was doing it on my tablet, and my first attempt, it crashed after I answered 3 questions, and so I retook it. And I was wondering if there's any way for that to be the grade for it. It was for chapter 3 quiz.
Yeah, I am fixing it right now.
At first, I thought it had let me like resubmit it, but then I realized you can take it as many times as you want for practice.
Yeah, so you said that was quiz 3.
Yeah, chapter 3.
Okay, I'll have to fix that.
Okay, thank you. And then I'm not able to stay for lab. I was wondering if I would be able to get the packet and do it again.
Yeah, I just haven't printed it out.
Is it on the, it's online?
Yeah, but I could print it out because I'm about to go print it out for the class. All right, if there are no questions on stream, I'm going to stop the stream. So you can just email me. Thanks for your participation.